Hello, cutie patootie, math angel. Welcome back. This is Decaf-Math ASMR. Today we are going to work through solving this differential equation using the Laplace Transform. Laplace Transform. And if you have no idea what I'm talking about, no worries, no pressure. There never is around here. It's Decaf-Math, so I hope that you can use this video to just relax, zone in and out, to play around with the parts that seem interesting, or that you can get some practice in, and just let the rest wash around you. Never mind it. You can drift off to sleep. Maybe you'll catch a tinkle or two. But if you are learning or trying to review, I hope that this is helpful for you. And we'll just kind of see where it takes us. We're just going to try and take a look at this example, okay? So, the first thing I did want to mention is that this is usually from a first differential equation class where you start to learn different techniques for solving certain types of differential equations. And a differential equation is simply an equation that involves a derivative. That's the base definition. So there are some more straightforward ones where you can simply use Calc 1 and take an integral to find your function. And there are more complicated ones where you have to do a bit of work. So the goal of solving a differential equation is to find the function that solves this equation. So when you're working in algebra, you're often solving for a variable or multiple variables, the actual values of them. In this case, we are looking for functions that have this property. So for example, here we have y prime prime minus y prime minus 2y equals 0. We're looking for a function, usually of time, that's the implied variable, where if we take the second derivative of that function minus the first derivative of that function minus 2 times the original function, I get 0. So we're talking about functions of time or x or whatever other variable you're talking about. But for this type of question, I'm given initial values. So these kinds of problems in general are called initial value problems, IVPs. So I want to find that function that satisfies this, but also have this y of 0 is 0 and y prime of 0 is 2. Okay, so this Laplace transform technique is just one way of solving this, but it turns out for this particular example, it also has a particular form. This is a Bernoulli equation, and I think I've made a video on Bernoulli equations before. It's been a long while, but I did, and so you can check that out as well. But this happens to have this special form. But today we are going to use the Laplace transform technique on this example and not Bernoulli. Okay, I just wanted to mention that ahead of time. So there's usually not just one way to work through a problem, but I thought this was a good first example because it's the first time I've done the Laplace transform like in an actual question on the channel. But we have mentioned the key formula for the Laplace transform, which is this negative st f of t dt from 0 to infinity, like this. We won't really need this exact formula today, but it's good to kind of see, I think. But the idea is basically that we are converting a function of time. Like we said, usually the variable for this function, this y function, is t. So we convert a function from time in the time domain to s, which is in the frequency domain. So there are a lot of applications of this in engineering, for instance, but I'm a math gal, so this is my jam. This is the key formula that I like to look at. So basically you put in a function of time here, and you multiply it by e to the negative st, but we're taking the integral with respect to time from 0 to infinity, but we're left with this variable s. So when you do this entire function, you're taking the Laplace transform. So the key technique here that we're going to use is we're going to take the Laplace transform of this side and this side. So that means that we can take the Laplace transform of each part because it is an integral. So this is linear, which means we are able to, like an operation, it's a linear operation. So that means we can take the Laplace of this minus the Laplace of this minus 2 times the Laplace of this, and it equals the Laplace of 0, which is just going to be 0. So what we're going to do is convert this entire question into a function of s and solve in the frequency domain the Laplace of the function of time that we're looking for. Then we're going to use the inverse Laplace to find what the original function should be in the time domain. Does that make sense? I hope so. If not, we'll do all the work here in a second anyway. But that is why I have this table here. It's a table of Laplace transforms, and basically we have functions of time, and then the s, which is the frequency side. So it is a little overwhelming to look at first, I think. So I will read this out probably in another sleepy, relaxing video. But for now, I'm just going to highlight the fact that this is going to be the main piece that we're looking at, as well as the first derivative and second derivative properties from this equation. Let's actually prove this. I think I proved one before, that 1 is 1 over s by plugging into this and taking the integral. But we're just going to reference this part today, okay? So we can just kind of trust the table today. And like I said, we can go into the table in a little more depth another time. But let's get through this example and see if we can actually get a solution. So what function of time gives me this property as well as these initial values? Okay, so like we said, we're going to take the Laplace transform and we can take the Laplace of each part, just because this is the Laplace transform and it's an integral, and we can just go ahead and take the Laplace of each here minus the Laplace of 2y equals 0, which is the Laplace of 0. So what that means is we're just going to do this piece by piece. So the Laplace of y prime prime is from this s squared, and this table says f of s, but I'm just going to do y since our function is y here. So we're going to do y of s. So note that y of s, capital Y of s, is going to be the Laplace of the little y of t. Okay, so if we can solve for capital Y of s, then I can take the inverse Laplace to get my original function, which is what we're going to solve. But we're taking this entire equation and moving it into the frequency domain by using this. So s, and then instead of f of 0, I'm going to do y of 0 here minus y prime of 0. So I'm just changing the function names around, but the property still holds. S squared times y of s minus s y of 0 minus y prime of 0. The capitals matter here. So this is the Laplace of y prime prime. This is kind of hard to see, but it's f prime prime here, so y prime prime of t. Okay, so that's the first part. And since I did mention Bernoulli, I suppose the difference here is we're doing the Laplace of each part, but if you're doing this with using as a Bernoulli equation, you would use the characteristic polynomial here. So you'd have like an r squared minus r minus 2 equals 0. Okay, but you can kind of see a little bit of this pattern: s squared y of s minus s y of 0 minus y prime of 0, then minus the Laplace of y prime, which is s times y of s minus y of 0. So we're using this line here. So again, I'm going to use the y variable instead of f here, but it's the same idea. S f of s minus f of 0, and this is f prime of t. So in here I have y prime, and that implies y prime of t, right? So we have that for this minus, and because it's linear, I can pull out this 2, and then I have 2 Laplace of y, which is simply y, capital Y of s. So I have minus 2 capital Y of s, and this equals the Laplace of 0, which is just 0, because it's just, that all goes away, right? Integral of 0 from 0 to infinity is still 0. So now we've converted our entire equation from time to s. Okay, so now we're working all in terms of s, and what I'm going to do is solve this equation in terms of for y of s in terms of s. It's a function of s, right? So, but at this point, I can go ahead and plug in my initial values. So my little y of 0 is 0, which is nice. That goes to 0. Y prime of 0 is 2, so this is 2. And then we have y of 0 again. Here is 0, so that goes away, which is nice. So that just cancels out. And I think that leaves us with just s's, y of s, and a constant. So let's see what we get when we clean that up. So we have minus 0, that goes away, minus 2, minus, this goes to 0, but normally I would have to distribute this negative, but this is 0, so that goes away. So we have minus s, y of s, minus 2y of s equals 0. That is what's really fun about a lot of these differential equations, is we're basically translating these diffie-q's into this algebra world, which is a lot more manageable, and then we go back into our function world. So whether you're doing that by a characteristic equation or through this, it's just much nicer to deal with algebra, right? Because here we have y of s, y of s, y of s, and then this 2. So we're going to factor out this s squared. Well, we're factoring out the y of s, so s squared minus s minus 2 times capital Y of s. And then I'm going to move this 2 over here. So I am doing a lot of algebra steps all in one. Take your time with this if you want to review. Of course, on my channel I have a lot of algebra videos, so feel free to check those out. But I assume if you are learning diffie-q, that the algebra part should be kind of okay, hopefully. But be patient with yourself here. I'm going to divide this s squared minus s minus 2 over to this side here. And then voila, I have solved for capital Y of s. So this isn't our answer yet, because this is all in terms of time, but this is in terms of s. So what I have solved is the Laplace transform of my function. So now I need to somehow take this back. Now that I have the algebra down, I have to take this back into my time domain, right? So what am I going to do? So I have this s function here. If I could look straight onto my table here and see something of this form, I would. And I would just go, oop, there's my function. So, oop, there's my function. But, spoiler 1 over s minus a is exactly what we're after. So I do have this fraction here, and we're going to have to use, I forgot what the method's called, I think it's decomposition, it's been a long time, but we're basically going to break this down. I believe it's decompose it into two different fractions of this form. So, like I said, we'll go ahead and read through these in another sleepy video so I can show you that this is not anywhere here, but you're just gonna have to take my word for it today. But because in this case I can factor this denominator, right? So 2 over s minus 2 times s plus 1. So I did want to mention that I am telling you that you have this form now ahead of time, and that's only because I picked this question on purpose to use this particular function. But if you're looking at some really complicated DFQ, the general idea is to take your Laplace transformed function here and try and somehow break it down into one of these forms, and get the inverse Laplace transform. So that's why this table can come in handy, but right now we're not really working with trig functions or hyperbolic trig or anything like that, or like a heavy side or anything like that. So maybe we can pick out other examples as well, but I'm just telling you now that this is of this form. We're going to try and break this down algebraically in terms of this 1 over s minus a constant, and then get that as e to the something t, which would look familiar had we done this using the Bernoulli function instead, that method instead. But I'm just telling you ahead of time, so you're just going to have to take my word for it now. But in general, it just comes through practice if you're trying to do this for school. But if you're just working through some random DFQ problem, hopefully that general outline can kind of push you in the right direction here. So basically you're doing this algebraically to get one of these forms. But like I said, there's a lot of them. It's very complicated. But we'll take a look again in a sleepy video, but also kind of look at other examples as well. But through practice here, I think this one is very clear that we can do this algebraically with just e to the at. So that being said, I'm going to try to break this one fraction down into two linear components. So we are going to, I believe it's called decomposition, but I can't remember. So basically we're going to break this down into the form a over s minus 2. Now that I've factored this, then I want it to be a over s minus 2 and b over s plus 1. So we take each of these factors and split them, and we just want to do this linear decomposition to get a and b so that I can find an equivalent here, so that I can take each part and do e to the at. I hope that makes sense. So let's see here. So when I combine into a single denominator, I just cross multiply, right? So I do a times s plus 1. It's basically s plus 1 on the top and the bottom. So I have a times s plus 1 plus b times s minus 2. And that has to equal 2, our original numerator. And so I just want to distribute everything. So this bit is algebra, and whenever you learn about decomposition, but you want a plus b to equal 0 because you have no variable, and you want a minus 2b to equal 2 because that's the constant part. So you have two equations and two variables here, right? And so you just solve. So a little something for our algebra friends. And I'm sorry if I get cut off a little bit, or if I have to start writing a little sideways. It's kind of hard to multitask, but I'm going to solve for a and b here, and I'm going to go ahead and subtract this from this. So I have b plus 2b, so that's 3b is 0 minus 2 is negative 2. Divide, so b is negative 2/3, and then a is positive 2/3. So I basically broke this down into 2 over 3 times s minus 2 minus 2 over 3 times s plus 1. Okay, so we just kind of have to trust ourselves here until the end, I think. We're almost there. So we basically have 2/3 and 2/3. So this is 2/3 times 1 over s minus 2 minus 1 over s plus 1. So, okay, so that's it. That is my, that is still my Laplace transform of my function, but written in a way so that we can get our inverse Laplace. So again, from our table, I want to take the inverse Laplace of this to actually get y of t. So this is the Laplace transform of my function. So when I do the inverse Laplace, I can still pull out the constant, and then this 1 over s minus 2 is 1 over s minus a, so a is 2 here, so it's e to the 2a. E to the 2t. And then minus, and then s minus minus 1, right? So a is negative 1 here, so it's e to the negative 1t, or just e to the negative t. So this is my final function. Y of t equals 2/3 e to the 2t minus e to the negative t. And that would be my answer to this question. So that function, 2/3 parentheses e to the 2t minus e to the negative t, here hopefully satisfies if I take the second derivative of that minus the first derivative minus 2 times my original function. Hopefully it equals 0, and if I plug in 0, I should get 0, and if I plug in 0 to the first derivative, I should get 2. So, we did it. Now, the fun part about all of this is in differential equations, if you're looking for a function that satisfies your equation, you can usually go back and check your answer. So even though you might not always get an answer, if you do get something and it actually works in this, then you at least know that your answer is right. But hopefully this one works out. I will actually confirm that it does and go through the steps here, but because that is more of a calculus and algebra exercise, I will make that in another video. Like, I'll record that very soon after this and use this function and check it with this, and hopefully it all works out. In fact, I'm going to go ahead and do that very soon before I post this, because I want to make sure that this is actually the right answer. But it does appear to have the same form as I would expect from a Bernoulli form, just because the characteristic example, or the characteristic equation, is r squared minus r minus 2 is 0, and you can factor that to be r minus 2 times r plus 1, which is very similar here. And then do the c1e to the root t part and solve for c1, c2. So the main part would be this 2/3 that I would have to check, but it looks promising. So I think we did well. I think this is correct. I would kind of try to trust myself here, but we're going to go ahead and check that in another video. But hopefully this helped kind of get you started if you are learning about the Laplace transform, to kind of get this idea. You're converting from this time domain where the equations can be complicated with these derivatives to an algebra world, this frequency domain where you're just working working with s and s squared here, and converting these derivatives into these exponents instead. So I hope that it's interesting. You solve in that algebra world and then take it back into the derivative world again. And I really enjoyed this throwback. And I did take this in high school and then again first semester freshman year to get the actual credit. So it's been a long time, but I find this to be very, very satisfying. And yeah, so I hope that this was helpful. I'm sending you much, much love. If you're asleep right now, I'm wishing you sweet, sweet dreams. If you're going to continue with the rest of your day,